Hey, physics friends. Welcome to 2.4, which I'm entitling your first physics equation. Over the course of this semester and this year, we're going to be using equations. They're just relationships between like force and acceleration. The harder you push on something, the more it accelerates. Boy, how is the period of a pendulum swinging related to its frequency? So today you're going to learn about how velocity, time, and displacement are all related. So we're going to define a few terms: velocity, average velocity, instantaneous velocity. We're going to look at a graph from our moving man to just talk about specific spots on this and how do they relate to those words that we just talked about. And that's where I'm going to leave it off today. I've got two example problems coming up that kind of get a little bit complicated, but I can use position versus time graphs to solve them. It's the classic, a car leaves Madison and a car leaves Platteville. How do you use position versus time graphs to solve those? And it makes it a lot, I don't want to say the word simpler because that's a bad word, but you can help you, it's like a pensive. It's a way to put down in a picture what your thoughts are, and it becomes a little bit more manageable that way. So let's get started. All right, let's first define velocity. And I think that we maybe already defined this. Velocity is how fast and in what direction an object is moving. It's a vector quantity. A vector means it's got a direction, north, south, east, west, left, right, forward, backwards, in the positive direction, in the negative. These are all ways to say direction. And you've got how fast associated with it. So there's some sort of rate, like distance and time. So miles per hour, kilometers per hour. Those are ones that you probably have heard of. Average velocity. Average velocity is your displacement an object moved divided by the time it took to do so. And I define displacement as wherever you start, take that away from wherever you finish. Your initial position and your final position, you subtract those two. It's always the final minus the initial. And then you're going to divide it by the time it took. Instantaneous velocity. Instantaneous velocity is the velocity at a specific point in time. It's not an average over the whole time period. It's at a specific instant. How fast are you going? And in what direction? It's defined as the slope of the tangent line on a position versus time graph at that point. Don't worry if all these words are confusing you, because I can see how seeing them the first time would be very confusing. So I'm going to do a bunch of example problems. You saw that in the next slide of me going through all of this. So what's important right now is that you just write these definitions down so that you can call them up later should you forget. And I promise you, you will forget. So I want you to write them down. Lastly, speed. Speed is just how fast an object is moving. Now, in the typical parlance of our time, we interchange speed and velocity, and they mean the same thing to normal human beings. You are no longer normal human beings. You are physics students. So you have elevated above the rest of the rabble in that there is a difference between speed and velocity now to you. Speed is just how fast, 55 miles an hour. Velocity is 55 miles an hour south. They are the same thing, but speed you just don't need to tell me a direction. So I'm going to get to your first physics equation right here, and I want you to copy it down with me. Simply written, your first physics equation is this. Velocity equals displacement over time. Now, I'm going to write it a little bit more complicated, and this is the way you'll see it if you ever go on or you see this equation. They'll write it like this. that bar above represents the average velocity. So if you ever see a bar above something, that means average velocity. Those triangles are the Greek letter delta, which represent the change in displacement, the change in time. And that's why you see me here when I talked about average velocity. It's the difference between where you start and where you finish, and the difference between your initial time and your final time. So sometimes you may see it even like this. D sub meaning below, like submarine, like D sub F minus D sub I over T sub F minus T sub I. So final displacement minus your initial displacement divided by your final time minus your initial time. Sorry, this is a little messy there. But a lot of times our initial time is going to be 0. And I'm gonna typically write it like this because it's not so intimidating when you see all these fancy words and physics talk. So let me show you how I would apply this equation to some, and these terms to some problems. So this is a graph that I grabbed off of our moving man, and I have 10 questions here, and we're going to go over these together. So number 1, it says, what is the average velocity over the entire interval? So remember, to find the average velocity, it's your total displacement, your change in displacement divided by your change in time. So how do I, over the entire interval, what's my displacement? Well, it's my final position, right? Now my final position is 10. My initial position was -10. So I moved 20 in the positive direction. That means if I start out here at -10, over the entire interval, I end up moving 20 positive. So that's why this ends up being a positive 20. And then the time it took me 10 seconds. Or my final time, which is 10, and my initial time, which is 0. So 20 divided by 10 is 2. So my average velocity over this entire thing is 2 meters per second. I'm being kind of flip about my significant figures in my problem, which I should be doing a better job of. So it should be 10.0 minus 0.0 and 10.0 minus -10.0. So using 2 significant figures throughout this whole thing. So my average velocity over this entire interval is 2 meters per second. So I'm just going to squeeze that back over there so I can get out of the way. Question number 2. What's the average velocity over intervals A, B, C, and D? So I just do this a little bit more in depth. I'm going to switch the width of my... So interval A, the distance that I travel, my displacement is +10. The time it takes me is 2 seconds. So that's 5. And maybe you recognize this as the slope from algebra class. That's exactly right. The rise over the run is also the velocity, the average velocity between 2 points. That's over interval A. Interval B, my displacement is 0. I'm not moving. So that is 0. I'm not moving, so my average velocity is 0. What's my, at C, I'm moving 10 and I'm doing it in 2 seconds. So that's again another +5 meters per second. And then at part D, I'm moving in the negative direction. So my final position is down here at 0. My initial position is up here at 10. And then the time it takes me, it looks like, half a second. So this is a negative. This one's going to be a negative 10 divided by 0.5 is going to be 20. So this is going to be a negative 20 meters per second. And I probably got to use two significant figures because that's what's going on down here, so I would be forced to write this as scientific notation. Negative 20. Now, with speed, the next question says, what's the average speed? The average speed and the average velocity are the exact same, except for the direction. So the average speed for part A is 5. The average speed for part B is still 0. The average speed for part C is still 5. But the average speed for part D here, this piece right here, it's not negative 2. The negative is telling you what direction it's moving. The average speed is a positive 20. Positive 20. So in a way, speed is the absolute value of velocity. The absolute value of velocity. Now let's talk about instantaneous velocity. The instantaneous velocity that we talked about, the definition is it's the slope of the tangent at that point. So right here, what's the instantaneous velocity at 1 second? So here's 1 second. What's the slope of the line right there? Well, it turns out that the slope of the tangent line at 1 second is the exact same slope as this right here over the interval A. So the slope of the tangent line is still going to be the rise over the run. So it's going to be positive 10 over 2. So positive 10 meters over 2 seconds. So that's going to equal 5 meters per second. So it turns out that at point A, the instantaneous velocity is the exact same as the average. And that's because this is a straight line. I could pick anywhere on this interval. Like I could pick the point 1.5 seconds. The instantaneous velocity there is also 5 meters per second. I could pick the point right here at 0.5. I'm moving at a constant velocity, a constant speed over interval A. So when you move at a constant speed, the instantaneous velocity is the same throughout. You're not changing speeds. You're not changing velocities. The next question says, what's the instantaneous velocity at 2.5 seconds? So now I'm going to look over here at the 2.5 second mark, and the velocity there is 0. The instantaneous velocity here is still 0. Because everywhere on the entire interval, the slope is equal to 0. If I were to go at 0.25 seconds, slope of that tangent is 0. If I go over here to 0.75 seconds, the slope of the tangent line is still 0. Question number 6. What's the instantaneous velocity over here at 5.2 seconds? Maybe you start to see a pattern. It's going to be that negative 20 that we found before. So what's the instantaneous? I'm going to just skip my sig figs here. Don't do what I do. It's still negative 20 because this is a constant speed because it's a straight line. And everywhere on this interval, I'm moving at the same rate. Now, where it gets a little bit crazy is that last interval, which is, I'm calling it interval F. So, hey, question 7. What's the instantaneous speed? The instantaneous speed at 5.2 seconds is 20 meters per second. Again, I skipped over my sig figs just for time sake, and I don't like writing all that, but you can't. Number 8. What's the instantaneous velocity at 7 seconds? So right here, This is really important. So at this point, the slope is at a 0. It's a 0 slope. It's horizontal. So the instantaneous velocity at 7 seconds is 0 meters per second. The slope of the tangent line at that point. What's the instantaneous velocity at 9 seconds? At 9 seconds, we are right here. That has a tangent line, and you have to do a little bit of estimation when you're doing ones like this. And I'm very flexible with how you draw your tangent. So I'm going to draw a tangent, and then I'm going to find the slope of that tangent. Right there. There's my tangent. Now I just have to find the slope of it. So I'm going to pick a couple random points. Let's see if we can do this nicely. Maybe I'll pick right here. So this looks like the point 7.5 comma negative 5. And then I'll do maybe this point right here, which looks like 10 comma 7.5. So I'm going to do the rise over the run of this tangent. So the rise looks like it goes up 5 plus, it goes up 12.5. And then it runs, looks like half, 2.5 seconds. So I'm going to pull out my calculator, and I'm going to take 12.5 divided by 2.5. And I get 5. What do you know? That's nice. So the instantaneous velocity right here at 9 seconds is 5 meters per second. It's the slope of that tangent line. And here you're actually seeing, the velocity increase. Because at the beginning, you saw the velocity was equal to 0. Right here, you saw the velocity equal to 5. I bet right here the velocity has something probably like 10. The speed of this object is increasing. And maybe you saw that with the moving man where we had curving lines. That represents that you're accelerating. And we'll get to that next chapter. But for right now, it's really important for you to know the difference between average velocity and instantaneous velocity. And then lastly, what's the average velocity from 7 to 10 seconds? So the average velocity, it's the change in your displacement. So at 7 seconds, I'm right here. So my final position is 10. My initial position is 0. My final time is 10 seconds. My initial time is 7 seconds. And again, I'm getting this from my displacement final minus my displacement initial over my time final minus my time initial. And that's equal to, remember that was that whole change in displacement over change in time, and that's your average velocity. So I'm getting these numbers from this equation that we defined in the page prior. So basically it's 10 divided by 3, so that's going to be 3.3 meters per second. So that's my average. My average velocity over this interval is 3.3. The instantaneous velocity is changing everywhere. The instantaneous velocity here was 0. The instantaneous velocity here we found was 5. Instantaneous velocity here we thought was 10. But the average over the entire interval is 3.3. All right, friends, this is where I am going to leave you today. Thanks for paying attention and getting these down into your notes. It's really important for us to know the difference between the average velocity and the instantaneous velocity, and then how speed is related to velocity as the absolute value. We'll see you later.